Wind turbine is a device designed to extract energy from the wind. My name is Wei Yu. I'm an assistant professor at TU Delft. This video will focus on wind resources. By the end of this lecture, you should be able to define wind energy and explain how it is quantified, describe how wind is generated by atmospheric process, understand the spatial and the temporal variability of wind, explain key characteristics of wind resources. What is wind energy exactly? Wind consists of countless tiny air particles, and each of them carries kinetic energy. The kinetic energy of a moving object is defined by half times m times u infinity square, where m is the mass of the object, u infinity is the velocity of the motion of the particles. To understand how much energy we can extract, we consider the mass flow rate. That is, the mass of air passing through the rotor area per unit time. This is given by rho times A times U infinity, where rho is the air density, A is the frontal swept area of the turbine blades. U infinity is the velocity of the air particles. The kinetic energy carried by this amount of air during a small time interval dt is defined by half times rho times A times U infinity cube times dt. We end up with that the power available in the wind is proportional to the cube of the wind speed and the air density and the rotor's swept area. This figure further illustrates how the available power from the wind changes with the wind speed. As you can see, power increases with the cube of wind speed. To keep things simple, let's assume air density rho equals to 1 kilogram per meter cube. Rotor swept area A equals to 1 meter square. With these assumptions, at a wind speed of 2 meters per second, the available power is 4 watt. But at 10 meters per second, the available power jumps to 500 watt. 5 times wind speed leads to more than 100-fold increase in available power. It shows how sensitive wind energy is to wind speed. This is why wind farms are typically located in regions where with consistent and sufficient strong wind. Have you ever wondered where wind actually comes from? It all starts with the sun. The sun hits the Earth's surface unevenly. Some regions receive more solar energy than others. This creates temperature gradients across the globe. As a result, warm air rises because it's lighter, cooler air sinks toward the ground because it's heavier. This movement sets up global air circulation patterns, large-scale wind systems that constantly redistribute heat and energy across the planet. On a smaller scale, local circulation patterns like sea breezes, mountain winds, or urban heat effects also play an important role in shaping the wind conditions at a specific site. Then, what's the distribution of wind globally? This wind speed map illustrates the global distribution of wind resources at 100 meters. We can see that coastal and mountainous regions typically experience higher mean wind speeds, roughly 7 to 9 meters per second, making them prime locations for wind energy development. In contrast, inland areas generally have lower mean wind speed, roughly 4 to 6 meters per second. Understanding this spatial variability is crucial for effective site selection and the turbine's performance optimization. Wind speed also varies at different time scales. This spectrum illustrates how wind energy is distributed across different time scales, with a period shown on the horizontal axis. The peak on the left shows long-term variations. that is, seasonal changes, which are driven by global shifts in temperature and pressure patterns over the Earth. A prominent peak around a 4-day period reflects the influence of moving high and low pressure systems over large regions. Daily variations are due to local effects like sea breezes and mountain winds caused by the day-night heating cycle. Short-term fluctuations or turbulence occur over seconds to minutes, are influenced by terrain, buildings, and surface heatings, etc. They cover spatial scales from millimeters to about kilometers. Among these spatial and temporal characteristics, I would like to highlight two important ones for wind energy harvesting: vertical wind shear and turbulence intensity. As wind approaches ground, its speed decreases, dropping from the undisturbed geostrophic wind at higher altitudes to nearly zero at the surface. This gradual change in wind speed with height is known as vertical wind speed shear. The shape of the wind shear profile depends largely on surface roughness, which varies by terrain. Different landscapes create different levels of resistance to the wind. In urban areas, buildings and obstacles increase surface roughness. This causes a steeper wind shear profile, meaning wind speed changes rapidly with height. Over flat, open areas like oceans, surface roughness is low. As a result, the wind speed is more uniform across heights with a much gentle shear profile. This means that ocean wind turbines often enjoy more consistent and stronger winds at high height, leading to better performance and higher energy output compared to many onshore locations. In this graph, you can also see many randomly sized vortex-type structures. These illustrate the turbulence, which describes the level of chaotic behavior in the flow, a feature we will explore in more detail later. What impact does wind shear have on wind turbine rotors? Let's imagine you are standing at one blade tip of a 3-bladed horizontal axis wind turbine, HOT. As the rotor spins, that blade tip moves through different heights, and at each height, the wind speed is different because of vertical wind shear. On the right, you can see the illustration of this sectional periodic wind speed pattern experienced by the blade tip during rotations. This variation in local wind speed means that each blade segment encounters changing aerodynamic forces throughout its rotation. This periodic fluctuation will lead to cyclic aerodynamic loads on the blade, which will increase the fatigue stress, therefore can potentially reduce the lifespan of the blade and the other components. Additionally, this non-uniform wind field can negatively affect power output. As we just mentioned, another key characteristic of wind resources is turbulence. This video shows how wind speed fluctuates across a modern wind turbine rotor plane when exposed to a realistic atmospheric boundary layer. These fluctuations are caused by turbulence, irregular and chaotic variations in wind speed and direction over space or time. Turbulence is typically quantified using turbulence intensity TI, which measures the level of wind speed fluctuations relative to the mean flow. The definition of TI is given here, where sigma U, sigma V, and sigma W represent the standard deviations of wind speed fluctuations along the 3 Cartesian coordinate directions, where U infinity is the mean wind speed. TI essentially tells us how gusty or unstable the wind is at a given location or over time. What's the impact of turbulence intensity on rotor performance? The animation on the left shows how one blade tip experiences fluctuating wind speed due to random turbulence and vertical wind shear. The right figure presents a time series of wind speed measured at 2 points, hub height. Fluctuation here are caused solely by turbulence. Blade tip fluctuation resulted from both turbulence and wind shear. These random wind speed fluctuations due to turbulence can increase fatigue loading on wind turbine components, reduce rotor efficiency, affect power output, and control stability. TI doesn't just affect a single turbine. It also influences how the airflow behind the rotor mixes with the surrounding airflow. This has major implications for wind farm layout and energy yield, something we will explore in a future lecture on wind farm aerodynamics. Understanding TI is critical for turbine design and site selection. In this lecture, we have learned what wind energy is and how to quantify it, how wind is generated, how wind changes across locations and over time, key characteristics of wind and how they impact wind turbine performance,